Hello and welcome everyone to the third Consciousness and Reality Colloquium for this academic year. I'm Kunal Mule, an astrophysicist and the co-founder of IMIX, which is the Institute of Mind Intelligence and Consciousness Studies. Our co-host today is Stuart Hameroff, who is an emeritus professor of anesthesiology and psychology at the University of Arizona. And our participants are from across Caltech, MIT, Stanford, and many other institutes, including Oxford and Cambridge. The CNR Colloquium series seeks to inspire interdisciplinary investigation on topics like mind cognition, consciousness, and the nature of reality. So before we introduce our colloquium speaker, I again wish to remind everyone that there's a Q&A button at the bottom of your Zoom window and that you can post your questions by clicking on that button, and selected questions from that Q&A box will be taken after the talk. As has been the tradition, we are going to make this interactive and fun. I'm going to launch a poll that I'm going to request all of you to respond to, simple binary choice questions. So I'm hitting launch right now, and I hope you're able to see these two questions on your screen. First question is: consciousness may be linked closely with quantum states? Simple yes or no question. And question two: quantum computers hold the key to understanding mind and consciousness phenomena. I'm sorry, Hartmut and Stuart, but panelists are probably not able to answer these questions. Nevertheless, we will keep them up and running, and I will announce the results of the poll at the end of the talk. So keep answering away and keep asking questions as you hear our esteemed speakers give his talk today. And with this, I now request Stuart to please introduce our esteemed speaker, Hartmut Neven.
Thank you, Kunal. Hello, everybody. It's great to be here. It's an honor to introduce my good friend, Hartmut Neven, computing, computer vision, robotics, computational neuroscience, quantum machine learning. He studied physics and economics in Brazil, Germany, France, and Israel. He studied at the Max Planck under Valentin Breitenberg and in Ruhr under Christoph von der Marlsberg. Worked on his PhD was in robotic vision. He came to the U.S. and was at USC for a while, and then went to Google, where he started their visual search project and developed Google Glasses, Google Goggles, Google Lenses. And in 2006, he started the Quantum AI machine group there, working with D-Wave, bringing quantum computers into AI. And around that time, he invited John Martinez to join his group from UCSB and collaborate. And Martinez was among those who won a recent Nobel Prize, if I'm not mistaken, for related work. In 2016 through 2019, he worked on and developed the Google Quantum Supremacy Project, where they showed a project solved with a quantum computer, which could not be solved with a classical computer. He went on to work on quantum error correction, time crystals, and had a simulation of a time crystal in his, I think it was a Sycamore quantum computer, traversable wormholes, the EP equals EPR idea. Non-abelian anyons, which have to do with topological quantum computers. And to top it off, Hartmut Neven has his own law that the performance of quantum computers doubles exponentially, which I'm glad to hear, because I think we all have them in our heads. So without further ado, let's hear from Hartmut Neven. Hartmut.
Yeah, thank you, Kunal and Stuart, for inviting me to this colloquium. Should be fun. So I will start here sharing. So I hope everybody can see this well. So I want to talk a little bit about work that I should explain is what we call at Google a 20% project. So the main mission of the Google Quantum AI Lab is to build a useful quantum computer for otherwise intractable problems. But as a sort of guilty side pleasure, I'm quite interested whether quantum processes need to be considered when trying to understand questions related to consciousness. So what I would like to start with is just the basic observation that, because we're all aware of it, there's tremendous success artificial intelligence is enjoying. Yet there remain open questions concerning natural intelligence, or I should rather say natural sentience. So these basic questions: what generates conscious experience? Do we possess free will? These are to date not answered by physics, nor by neurobiology, nor by computer science. And just to get this out of the way, when talking about this, often asked, how do you define consciousness? So my definition is pretty basic. Consciousness is our subjective first-person experience of the world. So conscious experience is what it feels like to smell a rose, suffer a toothache, or reflect on a memory. So when you want to construct a theory of consciousness, then any scientific attempt is then to explain it is really tasked with reconciling two perspectives of the world. One is the third-person perspective of science, and then there is the first-person direct experience of the world. So we need to bring these two perspectives into congruence. And if you are a materialist, or these days a physicalist, then, as opposed to, for example, a dualist or idealist, then you are tasked with stating which physical process implements, in modern parlance, a conscious moment. And of course, you have to take this out of the realm of philosophy or religion. You have to propose experiments to test your conjecture. And that is what my talk will be about. I want to explain a research program that starts with stating a conjecture: what constitutes the physical correlate of consciousness, what implements it. And then I want to suggest a sequence of quantum biological experiments to test this. And then, sort of a bit as bonus, I want to explain if our ideas are correct, then we should be able to shape the conscious experience of a user, so of myself or of you. And the tool to do this would be a brain quantum computer interface. And lastly, if time permits, I want to also talk a little bit about agency and free will and how this figures in our theory. So let's start with the conjecture. What constitutes a physical correlate of consciousness? So understand this is an interdisciplinary audience, so not everybody here may be intimately familiar with ideas from quantum physics and quantum computing. So we'll explain a few basics, but before getting to those, I should state, so it was very apropos that Stuart gave us a kind introduction, because I have to say that my thinking on these matters is strongly influenced and actually builds on the work of Roger Penrose and Stuart Hameroff. And this story really starts with Roger's seminal book, The Emperor's New Mind, was published in 1989. And there Roger made the following proposal, that a conscious moment occurs when the quantum mechanical wave function of a system collapses via a process he calls objective reduction. I will, as I said, in a moment explain what superposition states are. This is a key notion. But this proposal, or later then, was picked up and refined by Stewart, who added a biological mechanism where in the nervous system could such processes occur. And he suggested that microtubules would be the place where this would happen. But overall, I think George Musser, a science journalist, I think was in Scientific American or New Scientist, he wrote a nice article about this work and observed that it often is presented a little bit as a package deal, in the sense that there are several ideas that come together. One is, as I said, a conscious moment occurs when a wave function collapses. That's one piece. The second piece, Roger doesn't just use standard decoherence theory, but he adds non-textbook elements that suggest that gravitational influences cause this collapse. And then the third is the biological elements, the microtubules. So when trying to think about how you would test it, and I will, of course, get to, was inspired, how could you possibly test this theory experimentally? And then over time, I realized that really the nugget of this theory I like the most is what I like to call the generalized Penrose hammer of conjecture. And this is stating consciousness is how a system experiences the emergence of a unique classical reality. So this is, I think, out of sort of this body of work, the key element that I would like to preserve and elaborate on. Let me explain further, but maybe before doing this, quickly asking why should we at all consider quantum effects in neurobiology? People would say, oh, it's a macroscopic system, and it's warm and wet, and it's not an environment where naturally would expect quantum effects to be pronounced. But we should observe there's now a field called quantum biology, and it's quite active, and there are various phenomena have been identified where we believe or have evidence that quantum biological effects play a functional role. For example, magnetoreception in birds is maybe the most studied, or where we have most evidence. A second argument would be that life, when it started out in some primordial puddles, had to solve like early single cell or proto-cell organisms, had to solve essentially quantum computing tasks. You know, if you follow a chemical trail to find food, or keep a bilipid membrane together so that the cytoplasm doesn't spill out, and so at that time, the actions describing those systems were really close to Planck's constant. And one thing we know about evolution is that once a trick has served life well, it tends to be preserved. And third, of course, as quantum computing people, we have a long list of things that are useful, or are useful for tasks relevant to organisms, that will use quantum resources. And of course, evolution may have discovered those. So for example, we know that various sensing tasks can be done much better with quantum resources. And I often watch, let's say, the oak trees in our canyon here in Southern California, how they survive in very barren terrain. How do they decide, you know, where the roots should go to find water? I've read that about 16 different sensory systems have been identified and described in root systems. And I can't help but thinking that in such situations, quantum mechanical tricks would help with the necessary sensing tasks. But now, understanding why quantum physics offers a nice opportunity to place consciousness in a physicalist theory, let's look at the following. So if we have a simple system, a system, let's say, consisting of 3 coins, in a TED Talk-like situation, what I like to do to explain superposition, I throw like 3 coins on the table and say, look, this is to a modern numerical physicist is a 3-bit system. Each coin is heads or tails, 0 or 1, if 3 of them. So we can make 8 different states, and we start, let's say, in one state. And then in classical physics, how we describe the world is we have an initial state of the system. Then we know, let's say, the forces that act on the system. And then the system goes from one configuration to another. For example, somebody comes in and flips a coin, then the system state changes, may change again and again, but you go from one definite configuration to another. Yeah, so you have the system is moving on rails deterministically given known forces acting on the system. As opposed to this in a quantum system, a system state can go into a complex superposition of different classical states. And these in turn can go into superpositions yet again and yet again. So it becomes essentially this tangle of paths a system can take, but all these paths are taken simultaneously. We refer to these paths as Feynman paths, and we have to look, each Feynman path is associated with a number called probability amplitude. It's a complex number, and if you want to know what the probability is to see one of those states later on, you have to add up those amplitudes, and because they're complex, they can constructively interfere, and they can also destructively interfere. So that creates ultimately the probabilities with which we will see a state. So here already shows sort of this basic possibility. Essentially, quantum mechanics describes a system or the world as consisting of many classical configurations, yet consciously we seem to experience only one classical configuration at a time. So that then goes back to this generalized Penrose Hameroff idea that maybe this is how it hangs together, that consciousness is how we experience the emergence of a single reality out of the many that quantum mechanics tells us there are. So our life destiny would then be just one, or life trajectory would just be one Feynman path along those many. So I just described an abstract system and consisting of 3 bits, or if it becomes quantum, of 3 qubits. But of course, a brain is a much more macroscopic object, and hence the question would, of course, not implying that the whole brain per se, or it's necessary that we have superposition states involving the whole brain. Nevertheless, it's maybe important to appreciate the fact that quantum mechanics, even though the effects of quantum effects are easiest to observe in well-isolated systems, microscopic systems, quantum mechanics, as far as we understand it today, works at all scales, including macroscopic scales. So here I took the liberty and take like Schrödinger's thought experiment, Schrödinger's cat experiment, and sort of updated it a little bit and made it sort of a little bit more humane. So in vision, you have a hermetically sealed box. And then instead of letting the cats have all the fun, let's go ourselves into this box. And then, so to not make it so scary, let's not use a toxin that gets released when sort of radioactive atom decays, as Schrödinger originally suggested, but let's just have an anesthetic gas spill into this box. So this is a setup, and in principle, nothing would prevent us from building this. So the challenge is really to make this box truly hermetically sealed and not exchange any information with the environment. But in principle, we could think of doing such an experiment. And then we could do certain specific experiments, like, for example, at some point, we could open the box and look what's inside. So when we do these experiments, what would we expect? I think the right way to describe this system would be to use unitary time evolution. So in the beginning, we have the atom in an excited and a decay state. It's in a superposition. And then there's a human initially awake in the box. But after some time evolution, the atom will decay. And then by unitary evolution, the system will go into a superposition with, let's say, atom is excited, human is still awake, or the atom decayed, some anesthesia came out, and the human is anesthetized. So there is a macroscopic superposition. So there are now two humans in this box. And then we could do a number of experiments. And for example, we could open the box. And I would predict there are only two things you're going to see. There you either find a human anesthetized in there, or the human is still awake. We could also have the humans, this is actually an original suggestion by David Deutsch, the human could send out a little letter and like push it out of the box. And the letter could say, hey, I had a definite experience, but for the purposes of this experiment, I don't tell you what the experience was like. Human could also report the full experience. And lastly, in a very futuristic experiment, we could envision that we had some very advanced technology that would allow us to do all the interactions that happened since the beginning of starting this experiment, that we reverse every interaction. So essentially, we run this experiment back in time. And I think we can be pretty confident what the outcomes of these experiments are. For example, when we do the time reversal, you would come back to the initial state where you started. Note that in the standard Dirac-von Neumann formulation of quantum mechanics, where you have at some point a collapse of the wave function when an experiment is performed, would not predict this. If you have not strictly unitary time evolution, but also time evolution described by a projector, you would not come back to the start state in time. But I would say if this is a hermetically sealed box, then we should expect that you come back to the initial state. And why I'm so certain of this, which also implies that in some intermediate time, there was a superposition, again, two people in the box, one awake, one asleep. And the reason I'm pretty confident about this is that we can model this experiment that I just described. Again, it's difficult to do technically because it's hard to make a hermetically sealed box. But, and again, this suggestion by David Deutsch, we could model this inside a quantum computer. So the radioactive atom are just modeled by a qubits that can have two states. let's say 1 is excited, 0 is decayed. I pick a set of qubits and I call them the quantum AIs. That is the model for my human. And then if I have to send some affidavit letters reporting on experiences, I can do this with an affidavit qubit. And maybe earlier you wondered why I wanted to do this time reversal experiment. Yeah, because time reversal experiments are something that we routinely do in our lab. You might have seen our Nature paper like 2 months ago, the quantum echoes paper that used the time reversal protocol in a very prominent way. And so in this setting, I think if I would ask my team, what are the outcome of these different experiments? I think nobody would have any doubt that there would be no dispute about what the outcomes would be. And there would be no dispute that in the middle of the evolution, there is a superposition state with at least 2 branches corresponding to the quantum AI having seen the initial qubit in the 0 or second branch having seen it in the 1 state. So in some ways, this is a pretty good model of the experiment I described before. And it is hard to make an argument why this model is not good enough. Maybe you say, oh, it's not macroscopic enough. But look, our qubits are not small. You can see our qubits with a raw eye. Actually, the Nobel Prize that was given to not just John Martinez, who co-founded our team, but also Michel Devereux, who is the chief scientist on our team right now. And they got the Nobel Prize for making, in a way, macroscopic atoms out of solid state materials. So we're essentially dealing with systems and put them into superpositions that are already rather macroscopic. So it's hard to argue why this wouldn't be a valid model to the experiment I earlier showed. So this is one reason why I think quantum computing should make us confident that macroscopic superpositions indeed exist. And in some ways, the fact that quantum computing works at all, that you can have certain computations done exponentially faster, is because we can touch a large superposition state with an exponential number of classical definite states that make it up, that we can operate on all those classical states simultaneously. That makes quantum computing work. So it's not sort of like a mathematical trick or some sort of like only description of the world. This must have ontological, these different definite states must have ontological reality. Otherwise, I can't see how our computations would work so fast. Maybe I skip this. This is a slide for Christoph. So now we can ask, if we want to follow this idea that quantum processes create conscious experience, or that the emergence of a unique definite reality is what makes a conscious experience, and we can maybe look at a little circuit and discuss which process is responsible for doing this. So we can have here a little 3-qubit system, which we take where we take a first qubit into superposition, and then we entangle it with other states and make a larger superposition, and at the end we measure it. So which of these processes creates a superposition, do entanglement between the qubits, or collapse the superposition? Which process do we think is most suitable to implement a conscious moment? And here, going back to Roger Penrose, he suggested originally that if you collapse the superposition, this is where the conscious moment should occur. But if you think about this, there's a different pros and cons, to place consciousness at different spots, then you notice that there are some issues with this idea. And what's the issue? Is you can ask, okay, I measure, let's say here I made 0, 0 plus 1, 1, 1 state, and I measure, let's say, the first qubit, and I see a 1. Then in quantum computing world or quantum physics in general, you would say, okay, now you collapse the state. You now know it is the 1, 1, 1 state. But now you can ask, who feels what? Do all 3 qubits feel something, or only the qubit I measure? And here you see, Roger never discussed in any of his papers what happens to entangled systems. He always discusses this idea just in the context of a single electron, but never looks at several at once that are entangled. Because then you notice there is an issue with this idea. Because if we say the conscious moment is shared by all 3 qubits, then that creates a problem, because it opens the door to faster than light communication, which we know standard entanglement cannot do. That's textbook argument. But if you bring this new element, this sort of Bing moment, as Stewart would call it, moment of consciousness in that occurs across all 3 qubits when one is measured, then of course I could use this to make a Morse code and have superluminal communication. But if you go to the other place where we say, okay, maybe that's not exactly what Roger had in mind, it's just only the qubits that is measured feel something. But that's then very classical and takes one of the very attractive elements of this idea away, namely that entanglement can solve the binding problem, the phenomenal unity of consciousness. Moreover, if you say it's only the qubits that was measured, it has the ugly side effect that now, if then later you measure a second qubit, because already collapsed the superposition, then there can't be another conscious moment. So it's only the first qubit you measure, not the second. But which is first, which is second? Obviously, in special relativity, this would be it's frame dependent. So that version has the disadvantage that now who has the conscious moment becomes a frame dependent notion. So overall, I think it's problematic to follow this idea that the collapse produces, the collapse of a superposition implements a conscious moment. And I would advocate to sidestep these problems that we should go to the beginning, that when you create a superposition, this is when a conscious moment occurs. And so therefore, my conjecture and that of my co-workers is a conscious moment occurs whenever a superposition forms. For the experts among you, this requires that we introduce a preferred basis, because superposition is only defined relative to a basis. So I'm talking about Christoph Koch, when we discussed this, he suggests, okay, let's be super specific, let's write down some state transitions of a quantum state, and then write down who has an experience. So if the state stays the same, then there's no experience. If you make sort of a superposition of, let's say, with 3 branches, then the system can either become aware of, in this case, of the first branch, 1, 0, 0, or 0, 1, 0, or 0, 0, 1. So there's one of these experiences becomes now available. By the way, if the system is split and doesn't communicate across all qubits, then they're only sort of partial. You can't have then a 3-bit experience. You can only have, let's say, a 2-bit experience. So here, where it hangs a little bit together with IIT, IIT integrated information theory, and these ideas are really very complementary. And I feel it's in some ways rather trivial that if you want to have a 3-bit experience, your 3 qubits really need to hang together and shouldn't be separable in two groups, then you only have the possibility for fewer bit experiences. Okay, so this is the conjecture. I try to make it as definite as possible so that it can be falsified. So now let's use the remaining part of the talk to discuss how can we test this. And here I suggest a sequence of quantum biological experiments. And I should thank here, besides Google, of course, the Tiny Blue Dot Foundation funded some of the experiments I'm going to describe. And here's the experimentum crucis, the final experiment that we need to do. Because obviously one challenge in consciousness research is how can we even measure that something is conscious? Like when we have this debate, is the large language model, is that one conscious or not? We don't have a good protocol for deciding this question. So my example is always, maybe it doesn't need much illustration, but an illustration I like to use is a flight controller. You have an airplane, new airplane is constructed, and then engineers make a prediction about the airplane, like, oh, with this new engine, it will fly 1,000 kilometers per hour. Then any engineer knows how to test this prediction. You know, you whip out your yardstick and your clock, and you see how fast the airplane goes. But if you look at a flight controller and say, look, this flight controller has everything like a living creature has. It has sensors, it has input, it has actuators, can put the flaps or thrusts. It has memory, it has processing. Hey, is this a flight controller conscious? And then, let's say, people from the IIT camp, they could compute the phi value for the flight controller and say it's a phi of 1,000. But now you're stuck because there is no agreed upon measurement protocol that you can apply and check, is the 1,000 correct? So that's a limitation of conscious research, but there's a loophole. And the loophole goes as follows. There's one thing, actually only one thing, that I'm certain that's conscious, and that's myself, or you're pretty certain that you are conscious. And so there's your brain, that's my brain, and inside the brain, superposition states form and collapse. And so at any moment in time, or during, let's say, a second of my existence, conscious experiences should occur. And on a very fundamental level, let's say on the level of electronic structure, I think this wouldn't even be debatable, or we wouldn't disagree on this. So superposition states form, collapse. And of course, you can use a quantum processor, and that is made to create superposition states in a controlled way and measure them, collapse them. So one thing I can do now, I can expand my own consciousness, at least on paper we could do it, by coherently linking quantum degrees of freedom in my brain to the quantum processor. And now I have a wave function that straddles, let's call it psi-cyborg, that straddles the human brain and the quantum processor. And now I can make larger superposition states. Let's say if typically n biological qubits are involved when my brain operates, and I have m qubits in my quantum processor, now this superposition state would be spanned over n plus m qubits. And that I should notice. If this is, it's really true that the formation of superposition states now over a larger set of qubits, or if the formation of a superposition state creates a conscious moment, and if sort of the number of qubits involved there tells me how many classical bits I need to report on this experience, then if I use more qubits, the experience should be richer and I should feel this. Moreover, maybe by correlating user reports with checking into which state the system collapsed, I should maybe be able to find out which state feel how, and then such a setting could allow not only to expand human consciousness, it should also allow to shape the qualia of the experience. Okay, so this is, of course, a very conceptual experiment. Obviously, we haven't done it yet. It's very complicated, but we're working our way up to doing it. And so actually just a mile from where the Quantum AI lab is in Santa Barbara, there's University of California, Santa Barbara, and there's a group that works on brain organoids. And some time ago, we had a meeting and a good encounter. And essentially from this came the idea that we could possibly use brain organoids as a platform to study these ideas, where it's, of course, much easier than working with human brains, to see, could we couple synthetic technical qubits to qubits in an organoid? For example, would it be possible to mediate entanglement between two technical qubits across an organoid? Is that possible? If you think about it, also this is a very complicated experiment. By the way, here for those who are not familiar, brain organoids are these lentil-sized balls of generic cortical tissue. And a nice thing about this is here you see those. You can very well instrument them. You can do 2-photon microscopy. You can grow them on high-density electrode arrays. So there's a lot of signaling that you can extract from organoids when they're operating. But then when I discussed this with physicists involved there, like Dirk Baumeister is one of the physicists operating this lab. And then I question, okay, how do you exactly want to couple? Do you want to use photons, or do you want to use spin degrees of freedom? How exactly will we do this? And then we settled on the following baby step experiment. This was actually introduced or motivated by Stuart, who pointed me to, at the time, quite obscure, still obscure paper that claimed that, it's by Lee and al. It's actually this paper. So that paper claimed that different xenon isotopes have different anesthetic potency. And that's quite an interesting claim. First of all, what business does xenon have to be an anesthetic? It's an inert gas. Normally we learn they don't like to bind with anything. Why is this anesthetic in the first place? And goes to the general mystery of anesthesia. We use it since 180 years. Still nobody knows exactly how it is working. There are many things that have anesthetic properties, and they don't seem to be common chemical motives, suggesting maybe anesthesia has more to do with physics than with chemistry. Moreover, any anesthetic works across the animal kingdom. So an anesthetic that works on you will work on fish or singular cell organisms, and you can even anesthetize plants. So it must be a very basic phenomenon. But moreover, if it's really true that isotopes have different anesthetic potency, that really points to the fact that quantum processes need to be considered when studying this. And so what we started to do is essentially xenon isotope experiments on brain organoids, but we also wanted high statistics behavioral data. So we do this is Luca Turin and Ekin Daplan at the University of Buckingham in the UK. They exposed Drosophila fruit flies to isotopes. And then one thing and I should really, I only have this one slide sort of giving you a preview of the results, because the students working on this should really be the ones presenting it. And we are not quite ready to do the publications yet. Certain things that we do see nicely, for example, when you have a healthy organoid and you just measure its activity, you see this bursting activity. So here this axis is time, and then each line is a different neuron, and then each dot is sort of when it spikes, and you see that the spikes are nicely synchronized. So you have this synchronized bursting activity. And then if you give an anesthetic, then interestingly, the activity of a single neuron stays about the same, so spikes per second, but the nice synchronization falls apart. So this is something we see. So we have a nice indication how the anesthetic property works. And of course, now we are hunting to see differences in for isotopes. And the experiments that I love the most is because it's so simple that a high schooler can reproduce it, is the experiments with fruit flies, where essentially we have, I actually have a video that I hopefully can show here. So we put about, so we blind ourselves. So here this was isotope C. So the experimenters don't know which isotope it is. There are 40 flies in this syringe. And then initially it's only air in there, but now we push the plunger in and push the air out. And then we, so we'll go a little bit quicker. So we push the air out now. And at some point, this is almost the air out. And then we close the valve here. And then now we connect the bag with the xenon isotope. And then we pull it in the isotope so that at the end we have 10% air so the flies can breathe and 90% of an isotope. And then at 1 atmosphere of pressure, this mixture is barely anesthetic. But if you now push the plunger in, so here it shows after this happened, then the flies are anesthetized and are lying around there. And now we decrease the pressure. By the way, when it was all the way in there, was about 3 atmosphere of pressure, so they were asleep. And now we are pulling the plunger out, so the pressure decreases, and you see within seconds the fruit flies are starting to buzz again. And now what we can do is to see whether for different isotopes they start to buzz quicker or whether it takes them longer to wake up. And all I want to say at this stage is that we do have statistical significance, and we can show good p-values that indeed there is a difference between the isotopes that we are studying. The reason we are not quite ready for a publication yet is that we found after some time that the fruit flies, I want to show this, the fruit flies are acting as a swarm, meaning we can see that like a swarm of birds, a flock of birds, that at some point they all go quiet together, and then at some point they all buzz together. That's of course per se not a problem for this experiment, but it ruins your statistical power. So when you have 40 fruit flies in there, you don't get 40 independent trajectories that you can analyze, but you really get only one trajectory, the blob of flies moving around. So we'll have to repeat this experiment with single well dishes where sort of you have one fruit fly per well and improves the statistics. So we still need to do this kind of work to show that we really have this effect, because big claims require strong claims require strong evidence, and we want to still collect this. Okay, so there you have a sense how sort of the first baby step experiment to understand what would be good quantum degrees of freedom? Are quantum degrees of freedom at all relevant here when knocking out consciousness? Seems to be the case, and then from there we can possibly build connections between synthetic and biological qubits. Okay, so with that, I think I will probably stop. I'm out of time. I already went over time, so the last two sections I leave out. I think this idea here I have already explained. So I will pause here. And yeah, my key message was we have this conjecture when quantum mechanical superposition states form that implements a conscious moment, and this is an experimentally testable idea.
Thank you very much, Hartmut, for that fascinating talk. We have plenty of questions from the participants, and we had over 120 or 130 participants all throughout. So yeah, exciting. I said that I would share the results of the poll, so let me do that quickly. I'm going to hit share results. Okay, I believe you all can see this on your screen. The first question was consciousness may be closely linked with quantum states. 94 participants answered this question, but 67% answered as yes, and 33% answered as no. Second question was quantum computers hold the key to understanding mind and consciousness phenomena. 35% of the participants think yes, that quantum computers do hold the key for understanding these phenomena, and 65% think no. So thank you very much. This was a fun poll. I'm going to stop sharing now, and let's go to Q&A. While the questions are still trickling in, I'm going to let Stuart maybe take the first question.
Yes, thank you, Kunal. Thank you, Hartmut. That was really great. Very interesting. So, three quick comments about the your rejection of collapse because of the faster than light. That objection has been raised since Einstein's spooky action at a distance. Yeah, and yet EPR has been shown thousands of, if not millions of times. And I was at the Royal Society meeting in 1998 with all these EPR experiments were demonstrated. It had been 10 years since Aspect, and all these guys showed entanglement between mountaintops or off the satellite and this and that. But nobody could explain this, the thing that you just mentioned. How can you have faster than light processing? And Roger got up with an old-fashioned blackboard at the end and showed the EPR experiment. He said, if you make a measurement here on this, so they're together over here, and you send them here or someone, and then you make a measurement here, this one instantaneously changes. And he, with a piece of chalk, he drew it. He said, when you make a measurement here, the information goes backward in time to when they were together. And then this one over here remembers being in the complementary state. So you invoked backward time effect for something else. So why not use that to account for EPR, instantaneous EPR?
So, as I said, we understand well in quantum physics that creating an EPR pair and separating them space-like is not a substrate that allows for faster than light communication, because entanglement in some ways can be seen as a form of correlation, and there's no causation that can travel fast enough. But Roger is not staying with textbook quantum mechanics. He introduces this Bing moment, and then I asked if the Bing moment is shared between the two parts, which again is an extraneous element that normally in quantum physics we don't discuss. Then you can use this shared Bing moment to make a Morse code and would break this impossibility of faster than light communication. As to Roger's argument that, oh, I can have a backward in time effect, again, I'm not proposing such new physics. I mean, of course, this is very heavy lifting, to say, oh, there's a backward in time effect, to really see whether physics can be built consistently with this new assumption, which is rather dramatic, remains to be seen. But in my conversations with Roger, as I pointed out to him, look, In a quantum computer, I can't possibly do this if at the end of the day, at the end of a computation, let's say I run Shor's algorithm, and at the end I get the result, so I've collapsed it. If then the argument is, oh, the superposition never really happened because it was retroactively destroyed in the beginning where it formed, that doesn't work. I have the result, I have the factors of the big number in hand, so that's only understandable if in between superposition states formed. So I don't think it's a consistent suggestion to say, oh, no problem, we just postulate a backward in time effect. I think this doesn't quite work.
Thank you. I'll yield. I have some more questions, but I'll give other people a chance.
Yeah, we're going to have a lot of time, maybe later after this colloquium is over. And let's begin with this question asked by Daniel Belizkian, believe he's from UCLA. Due to continuous existence of the proposed qualia during the survival of entanglement as opposed to momentary existence of qualia during collapse in ORC-OR, your theory is able to integrate with generalized pilot wave theories. Have you considered a pilot wave framework for your conjecture, and where the emergent qualia are anchored to a non-local variable like John Bell's, Weebles, and in the system?
No, I have to confess that I always wanted to think this connection through more carefully, but I'm delinquent there and haven't done this yet.
Next question, Amok Singhal asks, would it be easier to modulate the senses observed by any individual rather than modulating their brain as a whole? I believe he's drawing a connection between would be changing what the retina sees versus via quantum computing rather than interfacing with the brain directly, or do you need both?
I have thought, like, of course, when you see this conceptual diagram of linking a brain to a quantum computer, then of course all sorts of questions come to mind, like how would you realize this? But then as we go forward with our experiments, you realize what you really need is make larger superposition states. How can you make larger superposition states? For example, we could potentially work with things like hyperpolarized xenon or so on and do it that way. By the way, I have a conjecture that this may be the important in the explanation how psychedelics work. Maybe the aromatic rings that characterize most psychedelics, maybe there are sort of, or two of them connected could be a biological qubit, and essentially what happens, you chuck down a glass of qubits, and that way larger superposition states form. So there may be other ways to test the idea, to go back to the person who asked the question, than doing a full sort of, let's say, MRI, NMR style linking of quantum processor to quantum degrees of freedom in the brain.
Thank you. Paul Skokowski from Stanford asks, regarding the fruit fly experiment, does the pressure affect the flies simply with oxygen and no xenon? And there is another participant who asks, what are your thoughts about the hypothesis that in your fly experiment, the only reason why the flies stop moving is because of the limited oxygen at high pressure rather than any anesthetic effect of xenon?
Oh, trust me, the group I'm working with, they are like super precise. So we have double checked in so many baseline experiments. So no, if there's only oxygen in there and I push it together, they are still buzzing around. Actually, you can see this in the video. We have also checked the pressure effects for the organoids, for example, with helium, which at the atmospheric pressures we are working with, 1 to 3 atmosphere, has no known anesthetic result, and indeed we don't see effect, and indeed we don't see it. So yeah, we have made all these control experiments, and now you need the xenon to put the flies to sleep.
If I can comment to support Hartmut, Luca Turin says that 10% oxygen, which is hypoxic in humans and animals, is okay with fruit flies. And apparently that's true. So I had that objection too, but they say it's not the hypoxia.
Okay, a very general question by Daniel is, what is the evidence that consciousness is special at all in the context of quantum mechanics? I.e., why could our consciousness not be part of a generally entangled state of the world without a special connection?
I'm not sure I fully understand the question. I would say nothing is maybe special about the brain in the sense that if you make this the suggestion, like, by the way, I should say that the experiments we suggest, they are in a way agnostic to whether Stuart and Roger are correct, that the collapse is what implements consciousness, or whether sort of our flavor, it's the formation of the superposition where we should locate consciousness. The experiments would in a way allow us to decide this, so we don't have to fully finish the debate right now based on first principles. This is testable. But going back to the question, what we can say, of course, the formation of superpositions and collapse of superpositions happens not just in the brains of higher mammals, but this is a process pervasive in nature. And these ideas naturally lead to a panpsychist view of the world, that we essentially live in a large organism that is conscious to various levels in all places, inside trees, inside the sun, inside your glass of water you're drinking.
Okay. One last question, and this is from my end, because I'd like to probe a little further on the theme of this series of colloquia, which is consciousness and reality. And one of the interesting statements that you made in the abstract is, if your conjecture holds, then the connection between the quantum superposition and consciousness should enable us to expand a subject's experience and shape the qualia associated with that experience, right? So, could you elaborate on that further, and especially in the context of what connection it really, or what further insights it would really give us on the matters of consciousness and what is the nature of reality?
Again, I think the only way to test a theory of consciousness is taking the only conscious thing you're aware or you can be certain of, that's your own conscious experience, and expand it, possibly shape it in controlled, predictable ways. So then you would probably trust, let's say, if you were to come to our lab and, I would very much like to do it with non-invasive methods, use MRI type methods, and then let's say you are participate in this experiment, and initially the link is not active, and then we talk and say, hey, Kunal, how are you doing? And say, oh, I'm fine. And how about now? Yeah, still okay. What are you talking about? And then I press a button under the table, establishing this link, and suddenly your typical n-qubit experience is expanded to an n plus m qubit. And actually there's literature, how many bits of conscious experience per second we have. There are different papers. They come to different estimates between 100 to 100,000 bits per second. I think that consciousness seems to be a little bit the executive summary of what is going on, or that's what we are most conscious of. And I would agree that the number of bits is probably not very large. So let's say order 1,000. And of course, our chips now have the size, and soon they will have millions. So you should definitely notice that now your conscious experience is richer, by which I mean that if afterwards you tell somebody about it, you would need more classical bits to report it. So in that sense, I would say this link between the brain and the quantum processor should allow us to expand or extend human consciousness in space, time, and complexity. And we should also be able to dial in the qualia. Or want to feel euphoric? Let me do the following. You tickle the superposition in certain ways. Or want to feel melancholic? Let me do the following. I think this should, in principle, be doable to sculpt the qualia in a predictable way. And if we could do this, then probably would say, okay, you must have understood something about consciousness.
Very nice. Thank you so much. Again, we are out of time. Just make a few announcements before we close. The next colloquium in the Consciousness and Reality series will be held on 21st of January. And this will be delivered by Paul Skokowski, who is the professor of philosophy and the director of the Center for Explanation of Consciousness at Stanford University. So stay tuned for more information on that. And in closing again, then danke schön, Hartmut, for that fantastic talk. Thanks to co-host Stuart Hammeroff, all organizers and participants who made this event happen. Have a great day, everyone. Take care now.
Thank you.
Bye.